Hi everyone, welcome back to Operations Research. Today we will use these videos to talk about dynamic games. Okay, actually this should be part 2, but anyway that doesn't matter. We have told you about static games as our first part of game theory. Today we will talk about another types of games, dynamic games. Our plan is to first give you some basic ideas, and then we will give you two different applications. One is about pricing in a supply chain. That means in a supply chain there are multiple players who will do the pricing decision, and we're going to tell you how that is a dynamic game. And then we will talk about indirect news vendor problems. You're going to see that it's an extension of the basic news vendor problems we mentioned several weeks ago. And again, there will be multiple players involved in. So let's start with basic ideas. Recall that we introduced the game Buck or Stravinsky or BOS to you. Okay, two players. If they both choose Buck, then the player 1 gets 2 and the player 2 gets 1. Or if they choose Stravinsky together, then they can get 1 or 2. But unfortunately, if they choose different things, then they will both get 0. Okay, that was a game, and that's a game that we introduced last time. Today, suppose the two players act or make decisions sequentially rather than simultaneously. We're going to ask what's going to happen here. Okay, so last week we say if they make decisions together, then there are all kinds of possibilities. Okay, it's not very easy to predict what's going to happen. Then we may want to ask another question: what if they make decisions one by one? Okay, there will be a leader, and then there will be a follower. The leader makes the decision first, and then the follower makes the decision. We want to act again. What will they do in equilibrium? And will the outcome become different? And what's the impact of the way they play the game? Okay, let's some discussions. So suppose player 1 moves first. Then instead of using a game matrix, now we also need to describe the order of a game. And typically that is represented by a tree. Okay, so we call this a decision tree or a game tree. Let's call it a game tree. In a game tree like this, there will be some internal nodes. Okay, for these internal nodes, there will be a label telling us who is making the decision. And then at each link, that label tells us what are the possible actions. So because we say player 1 moves first, so the first node or the first internal node tells us that player 1 moves first, and player 1 may choose B or S. And then it comes to player 2's turn. In either case, player 2 first observes what has been chosen by player 1. Okay, player 2 should first do that. Player 2 sees what has been chosen by player 1. And then player 2 can make her own decision, either B or S. At each leaf, we can say that both players have made their decisions, and then there will be two numbers, in this case two numbers, telling us what are the payoffs for these two players. If both of them choose B and B, then they will get 2 and 1. Or if they choose S and S, they will get 1 and 2. Okay, that's something we already know. Or if they choose differently, then they get nothing. So the payoff part and the decision parts are all the same. It's just that now the way or the timing for they to play the game becomes different. Previously they make decisions together, now they make decisions one by one, or they take turns to make decisions. Okay? The game will be played in general from the root to leaves. Okay? We will start from the root, which means the first player is going to make the first decision, and then try to move towards a leaf to see what will be an outcome. So let's try to solve this problem. Our question, of course, is how should player 1 move? And it turns out that player 1 should first predict how player 2 will respond. Okay, this is actually true in general. Even for a static game, when one makes a decision, he somehow needs to predict or somehow needs to estimate what the other player will do. Okay, here is the same thing. So for player 1, now this case is easy. Player 1 can first treat herself as player 2. So suppose I am player 2. What will I do in either case? If I see the other guy choose B, then for me to optimize my payoff or to make myself the happiest, I'm going to choose B, right? Because 1 is greater than 0. Or if I am in this situation, the first guy has already chosen S, then my best strategy will be to choose S. So if B has been chosen, choose B. If S has been chosen, choose S. We can say that this is player 2's best response. Okay, this is how player 2 should respond to player 1's decision. Okay, this is player 2's best response, or we can say it's player 2's optimal strategy. Okay, so with that, we can highlight player 2's strategy by using these thick lines. With that, we now can, player 1 can now decide what to do. Player 1 knows how player 2 will react, right? So based on that, player 1 can choose her own action. Player 1 will think, suppose I choose B. Suppose I choose B. I know player 2 is going to choose B, so I will end up with 2. Or if I choose S, I will end up with 1. So now player 1 will make her decision. Player 1 will choose B. And then we say BB will be an equilibrium outcome. So the thick line here tells us that player 1's optimal strategy will be to choose B. And then a thick line connecting the root and a leaf tells us what's an equilibrium outcome. It may be like this, okay, B and B. We also say this is an equilibrium path, right? It's a path from a root to a leaf. So this is an example in which we have exactly one equilibrium outcome. Okay, if you think about this game, player 1 moves first, and then player 2. So it's not very hard to understand that the equilibrium outcome will be exactly BB. We can perfectly predict the outcome because when the game is played dynamically. Okay, but of course not any game has this property. Sometimes we still have some games, some dynamic games, which have multiple equilibrium outcomes. That's again possible. Then at each at the root, you will see multiple thick lines telling us that player 1 may be indifferent among multiple options. That's possible. Okay, so let's do some comparisons. First, when we are talking about predicting their behaviors, in a static case, we cannot really predict what's going to happen. But for the dynamic case, we can. So that means their equilibrium behaviors may change when we change the game rule from static to dynamic. Okay, that's intuitive. But we still have some questions. First, the equilibrium behavior, does it always change when we switch from a static game to a dynamic game? We're saying that we have a static game. When we change the rule to make it a dynamic game, do these players always change their behaviors? Intuitively, the answer is no, right? So we're going to show you an example telling you that indeed it is no. Sometimes when you change a game to a dynamic game, nothing really changes. Again, we have another question. Suppose player 2 is the leader and player 1 is the follower. What will happen to this dynamic BOS game? It's very easy to, it's not very hard to do the analysis by yourself. Okay, make player 2 the leader and the player 1 the follower. Eventually you will see they will play SS. And that somehow tells us in our dynamic BOS game, the first mover or the leader has an advantage. Somehow it can optimize his or her payoffs. Okay, and that's something that you may convince yourself. Let's see another example. We have a prisoner dilemma, right? So we have these numbers as payoffs, and we know the equilibrium outcome should be denial and denial because they can, the equilibrium outcome should be confess and confess, right? Because they cannot agree or they cannot coordinate on the optimal or the most efficient outcome, denial and denial. Somehow they will be induced to choose S as C and C, confess and confess. So now let's think about this question. What if they move sequentially? Okay, intuitively, C and C is not good, and C and C comes from the fact that they cannot coordinate, they cannot communicate with each other. When I choose C or D, I cannot let you know my choice, so it's very hard to communicate. Now when we change the game to play dynamically, if I choose something, you will see it and you can make that decision accordingly. It seems to us that there are some kind of communications. Does that work? No, let's try to analyze it. Our game tree is here, so let's consider player 2. Okay, for player 2, I first think about if I have observed D, what should I do? So for D, I think here I get -1, here I get 0. Oh, -1 is worse, so I'm going to choose C in this case. Or if I have observed C, then I compare -9 and -6. I can see, okay, I should choose C. So now it's player 1's turn. Player 1 thinks, okay, there is D, there is C. For D, I'm going to get -9. For C, I'm going to get -6. So, okay, player 1 is going to choose C and C. So what does that mean? That means the equilibrium outcome is the same. In equilibrium, they will still both confess. Player 1 will confess first, and then player 2 will also confess. So they end up with -6 and -6. The outcome does not change. Okay? Even if they can see, the player 2 can see player 1's decision, that doesn't really help. Because for player 2, we know confession is just a dominant strategy. I don't really care about what you choose. What's important is that no matter what you choose, I should always choose confession. So that's why the outcome does not change. Even if they agreed to both deny, and the player 1 really denied as a promise, and then player 2 really sees it, player 2 should still confess, right? Because confess is the best thing for player 2 to do. So player 1's promise will be useless in this case. Okay, so we completed 2 examples about dynamic games. Somehow you get a feeling. If there are multiple players, moves one by one, we somehow start from the last player's strategy and then move backwards to the first mover's decision. That's true in general. In the next video, we're going to give that idea in a more concrete format. Okay. Again, I also want to remind you that we are assuming that all the players are rational. Somehow that means they don't care about the other guy. They only care about themselves. And each of them want to maximize his own or her own expected profits. Okay, that's some basic assumptions that we are always using. Okay, thank you.